So, welcome back to another workshop. Welcome back to workshop 8. And what we're going to do is we're going to carry on looking at vectors and planes and why do we need these in engineering? After all, the whole point of mathematics, to me, doing physics and engineering and such like, is mathematics is a tool. And we should actually have some reason for doing it. The mathematicians come up with beautiful mathematics which sometimes have limited applications at the moment, may have application 100 years from now. But vectors we've been using in engineering for well over 200 years now, so there must be some reason, and that's because things like forces are best described as vectors. And also things like velocity, areas, all sorts of interesting things can be described as vectors. So we've been dealing with addition, and remember that's nose to tail, just like dogs saying hello. We've done subtraction. We've done multiplication. Well, at the moment, as I was saying, there's three types of multiplication. There's scalar multiplication, where if you have an arrow, you just make it bigger or smaller, and no matter what you're multiplying it by. But we've got two other types of multiplication which you've been discovering. You've been doing dot products, and you've been doing cross products. And do these make a difference? Oh, let's do one of my favourite examples. I think Ian's borrowed it from me nowadays, but let's take it, let's do force, work, let's do work. So work equals force times distance. Well, you also have torque. Actually, in engineering, we usually call that a moment. The torque equals force times distance. Now, if you think about it for this moment, those are not the same thing. Applying a torque to something is not the same as doing work. So what's the difference? And the answer is that work is a dot product, and torque is a cross product. Now, what this means is that in this case, the thing about dot product produces a scalar result. So if we take that example up there, which I was talking about before, work is equal to force dot distance. What we end up with is an answer in joules, and joules has got no direction component. So what you end up with dot product, basically you end up with a scalar value, no direction applied. So often, what we used to draw them as here's A and here's B, and this is going to A cross B, A dot B, sorry, that's all very cool. Now, let's actually take this a little bit further, just because we can. If we go work equals force times distance, now they had this problem in an exam in high school many years ago, and they had person is walking along carrying a box, and the box weighs 50 newtons, and they walk 2 meters. And the question was, what was the work done? And this was actually in the this was like level 2 exam. And of course, if you know anything about work, if you've done physics, you realise that the force and the distance must be in the same direction. So because these are not in the same direction, the amount of work done is actually equal to 0. But they actually gave in the exam, the model answer, that the answer was 100 Newton meters, and that was wrong, very wrong. But the important thing here is the distance is important. So what we actually have to do is we have to measure the angle theta from the direction of travel. So what we actually end up with is work equals force times the cos theta. Isn't that cool? And if you look at the classic description of dot product, A dot B equals A, take the magnitude, times B, the magnitude of B, because direction is not important, signs don't matter, cos theta, you'll see that these are the same thing. Force times distance or displacement, cos theta. Isn't that cool? Okay, other things we do with these things is flux, magnetic flux is equal to the magnetic field times the area. I should put twiddles in here because these are vectors, that's not. Okay, what else? Power is equal to force, well, power is equal to work divided by time. So this is also divided by time, and distance divided by time is velocity. And again, that's going to be cos theta. Oh, sorry. P is equal to F dot V, which is equal to V dot V, times V cos theta. Okay, isn't that cool? You're probably thinking, oh God, he's gone crazy again. Okay, the other one we're talking about is cross products, because remember what we said, cross product, don't want to spend too much time, I'll let you do some problems here. You multiplies two vectors and results in a vector, and the result is a vector. And let's do that example I was doing before. Torque is equal to force cross distance. Cross product distance. And the thing about torque, yes, torque has a direction. Torque can either be clockwise or anti-clockwise. So torque itself has a direction. We also end up with things like if you have an electron flying through a magnetic field, the force on that force is equal to the Q, the charge on the electron, times the size of the magnetic field, charge is a scalar by the way, times the velocity, or cross the velocity. Well, can we tell that that's actually going to be a cross product? Yes, well, the answer is a vector, so this must be a cross product. And a clue to this is for a cross product, if you're doing this in engineering or physics or anything, there is usually a right-hand rule associated with it to figure out the direction of the direction of the force, of the direction of the resultant. So let's go back a little bit. I was talking before about magnetic flux. Sorry, just getting too carried away here. Flux, the flux is measured in Webers, is equal to B, the magnetic field, cross product, cross area. And what we were saying before, or actually that's dot, isn't it? That's dot. For a dot product, these both have to be vectors. That's not a cross, it's a dot. So is area a vector? And well, let's take an example. Let's take one of these cue cards I use. Does the area there look different than the area there? Does it look different there? Yeah. If the answer is yes, then it's a vector because the direction is important. If it looks the same there as there, then, well, it's a scalar. But so in this case, yes, it looks very different. So area is also a vector. Remember, we're talking the area of a plane here. So a plane itself, a bit of a plane, acts as a vector with a direction. And the direction is going to be coming perpendicular out of that area. This is one of the reasons why when we're working on planes, it's always nice to know where the normal of that is. So the area vector is always normal to the plane, and so if I have a plane here, I can show this by doing these little, looks like a virus of some description, I know, but so other places we use this in things like surfaces, and we use surfaces a lot, especially in computers, CAD nowadays, and all sorts of things like that. Path working, if you're trying to work out optimal stuff, gravities. If we're working out, we use planes, we're working out minimal energy requirements and gravity. And in fact, we actually have we actually have a name, a special name for the force that is right angles to the surface. We call that the normal force. We use it that often. We give it its own name. And I mean, this turns up all over the place. One of the most common places we use stuff in engineering is things like inclined planes. So if you put a box on there, you got the normal force acting at right angles to that. Boom, there we go, planes. And if you look at the simple machines, the classic basic machines of antiquities, a lot of them are planes. We've got levers, we've got planes, wedges, screws, they're all involve planes, and we use vectors from most. Anyway, we have some problems for you to do, so good luck on those.